This is the embedded system design class, and today we will talk about the serial peripheral interface, or in short, the SPI. Last time we covered the first of the communication protocol, which is the UART, and today we will check the second one, the SPI. Now, if you remember, the UART was asynchronous. The SPI and the I2C are actually synchronous. And all of them, they are serial interfaces. Now we will make a comparison between the SPI and the I2C before we cover the SPI module in detail. There are two synchronous serial interfaces on the big 24 microcontroller, the SPI and the inter-integrated circuit, or in short, the I2C, written this way or that way. Both are commonly used in industry. Now, this is a quick comparison between both of them. The SPI port require a minimum of 3 wires. Usually they are 4. It's full duplex, even though most transfer are half duplex. Its top speed is 10 megahertz. This is why it's best for high-speed serial transfer, and it's very simple. The I2C, on the other hand, uses only 2 wires, and it's half duplex, and the top speed is 1 megahertz. So comparing to the SPI, it's very slow. The SPI is actually 10 times faster than the I2C. So when do we use the I2C? If you want to reduce the external pin usage, then just use 2 wires, which is the I2C. Otherwise, pick the SPI because of its speed, of its high speed transfer. Now we will cover the SPI in detail. For the I2C, we're not going to cover it in this class, but by the end of this talk, you should be able to do it yourself. You can go back to the data sheet of the microcontroller and see how to work the I2C. Now, for the SPI, let's have this example to understand it better. Let's say that you have a microcontroller that needs to communicate with 2 other microcontrollers. So they are all big24. We have to pick one of them and we make it the master. The others will be slave. And now we have the 4 wires that we need to have. The first one is the serial data output. The second is the serial data input. And then you have the serial clock and a chip select. Now, since we are connecting with 2, you would need 2 chip selects. If you are having more than that, then you will have more chip selects. You will use 3 mandatory wires, and the optional one is the chip select. Now we will call them in short SDO, SDI, and S clock. As you can see here, if you have an SDO in one unit, it should be connected to the SDI of the other unit, if they are both microcontrollers. And vice versa, the SDO here will be connected to the SDI here. The clock, the master should generate the clock and then distribute it to all the slaves. Now for the chip select, you will have a chip select for each one of the units. So if you want to select this one, this microcontroller, you will make it chip select 0. Notice that it's active low. While if you want this one, you will activate its chip select, meaning the value would be 0. You can activate both of them if you like, make them 0, 0. You can activate only one, so you make this 0 and this one, or the other way around. Now, if you check the bin diagram of the big24, you won't see a special bin assigned for the SDO, SDI, and this clock. And this is why we use the remappable bits. For the SD out should be output. For the SDI, it should be input. And for the S clock, it should be output. Now for the chip selects, they are ordinary boards. So we picked up board B, and we picked up bit 3 for this one and bit 4 for the other one. It could be maybe port A or other bits of port B. That's also fine. So the SDO is for transmitting. The SDI is for receiving. You want to compare this to UART. We have duplex transmission. Actually, it's full. It can support the full duplex, but we will use it only for half duplex. You should know that this transfer is serial, and it will send the most significant bit first. And that's an example. You have an SDO, and you send the most significant bit, output 7, and then followed by 6, 5, 4, 3, 2, and 1. And now you have it as 0, and the total is 8 bits. And you can see the clock this way. You are clocking each one of the outputs. Now for the inputs, now this output is actually the output that comes from the master. And the input, this input, is the input received by one of the slave, let's say this one. So here, we chose to sample the inputs at the receiver side in the middle of the bit, which is the obvious choice. But the relation between the SDI and the SDO, you can see that at the end of the bit and the SDO, you actually start sampling the SDI in the other unit. There are actually many choices. The way this timing diagram looks, because we choose these bits, which is the clock edge, the clock polarity, and the sampling bit. Once you finish the communication, there is the SPI interrupt flag. It's 0 as long as you're still sending or you're not sending at all. Once you're done with the transmission, then you will raise the flag and you make it 1, with actually one more instruction cycle for the hardware, because you need the signals to move through the hardware. This is the general idea, but I should mention before we move to the next slide that for the chip select in the slaves, actually here we used RB3, and here we use the RB3 of the other microcontroller. It could be actually even different than that. Maybe RA and here RB7, could be any port. It doesn't have to be RB3. Okay, so now let's move to the hardware to understand it better. So in the hardware, just in general, a general look at it, here's the bus, and you can send or you can output data from the bus through some registers until you reach to this shift register, and you output that to the SDO pin that you mapped using one of the remappable pins. Or if you are receiving something in the SDI, then you have this Schmidt buffer to make sure the edges are sharp. You go through the shift register bit by bit, and then you send it through these buffers to the bus. That's the main idea. Now let's look at the detail. We need a clock. So internally in the microcontroller, the master microcontroller should generate the clock from the SCUI, from the frequency of the instruction cycle, or the FCY. It goes through 2 prescalers. The first one is the primary prescaler, and the second one is the secondary prescaler. We have 4 options in the primary, 1, 4, 16, and 64. And in the secondary, actually, we have 8 options from 1 all the way to 8. Since we have 4 in the primary, we need 2 bits. Since we have 8 in the secondary, we have 3 bits to select each one of them. And then we have a buffer that has the enable master clock to control it. And then you can send the clock. You can send the clock. This clock, you should send it to other entities. If this is the master, it should be sent to any communication unit. And also it should be sent internally to the shift register because you need to clock them one by one. So you select the edge, either rising or falling. There are certain specifications, the edge, the polarity, and the sampling. And these goes through these block diagrams until you control the shift register. And you probably have also sync control. Now, that's for the clock. The chip select or the SS here, again, it's one of the boards, and that you can use it to select the appropriate unit. Here we have the SDI and SDO. The SDI coming bits, you are receiving bits, and then it goes to the SPI shift register. If you are receiving, it will go to the SPI shift register. The first bit that you will receive is the most significant bit, and then you will shift it. New bit will come, and then shift it, you shift it, you shift it, until the most significant bit becomes here. So that would be bit 7, and in this position will be bit 0. Once you shift everything here in the shift register, it will move to the bus. So it will move through this direction here. So you have a buffer with certain control to transfer it to the receiver buffer or the SPI RX buffer. And from that, you send it also to the shared buffer that is called the SPI buffer. This buffer is very important when we code. So in the code, you will see that we always read or write to this buffer based on the direction. So here, once you clock everything and it's reached to the SPI buffer, now you can move it to the bus, and now you were able to read the SDI or the input, and you receive it into the internal data bus, which is 16-bit. Now for the transfer, actually before the transfer here, we have also a control for this buffer. Similarly, like this one here, we have also a control for it. And now for the transferring or transmitting from the data bus all the way to the shift register, and then from the shift register, bit by bit, it moves serially to the SDO output pin to move to the other unit. It's actually go from the data bus through this buffer to the SPI, for this buffer to the SPI buffer that you see here. And then from the SPI, this SPI buffer is actually shared for both receiving and transmitting. Now it moves also from here to the transmit buffer, the SPI transmit buffer, and then it goes to the shift register. And notice that all the communication from the data bus up to the shift register, whether it's transmitting or receiving, it's done in parallel. But from the shift register to the bin, it's done serially, bit by bit, and it has, it should be clocked using the clock that you selected here. So that's the idea of the SPI. We said that we will use it as half duplex. However, there is a support for the full duplex. So as you are receiving, you are also transmitting. There is actually support for that. That's what we said here, that the SPI is actually full duplex, but we will use it as half duplex. So now let's understand the primary prescaler and the secondary prescaler in detail. So here, the dominant equation for the SPI communication is the S clock or the serial clock. It's equal to the frequency of the instruction cycle divided by whatever prescalers you choose. So if you choose the prescaler, the secondary prescaler, and the primary prescaler, both of them 1 and 1, then the S clock is exactly as the FC. However, it's supposed to be less than the FC. The frequency that that is used for the instruction execution, it should be faster. The frequency of sending information bit by bit through the SPI should be much slower than the FCY. So usually you know your FCY and you know the frequency that you want to send your byte serially in the SPI. But the things that you need to find out is the S pre value and the P pre value. Now, for the P pre, we have 4 options since it is 2-bit. From 0, 0 all the way to 1, 1. If you use the code 1, 1, then the ratio or the prescale ratio is 1 to 1. If it is 0 to 1, then it's 4. If it is 1, 0, then it's 16. If it is 0, 0, then it's 64. And be careful of this. It's like the other way around. Maybe you thought that if the code is 0, then it's the least prescaler ratio, which is 1. No, it's actually the other way around. So be careful of this. If it is 1, 1, then the ratio is actually 1. 0, 1 is 4, 1, 0 is 16, and 0, 0 is 64. For the secondary prescaler or the S pre, same way, but here we have 8 options. From 1, 1, 1 all the way to 0, 0, 0. And again, you start 1, 2, 3, 4, 5, 6, 7, and 8 going down. So 1, 1, 1 would be the ratio 1. 0, 0, 0 would be the ratio 8 to 1. Okay, so what should we do when we calculate, when we try to find the S pre and P pre? Again, one equation and 2 variables. So what we will do, we will assume the P pre since it's only 4 options. And based on the P pre, we will try to find the S pre value. Now, at this point, we need to figure out the other bits. We said earlier that this waveform, timing waveform, is actually, it's just an example based on some choices: clock edge, the clock polarity, and the sampling. So to understand all kind of waveforms, what kind of setups that we can make, we should look at this SPI transmission formats. So for the clock polarity and the clock edge, let's define them first. The clock polarity, if it is 0, then the idle state for the clock is the low level, and the active state is the high level. If the value is equal to 1, then the idle state for the clock is the high level, and the active state is a low level. That's for the polarity. And we had between the polarity and the edge, if you take all the cases, you would have 4 cases: 0, 0, 0, 1, 1, 0, and 1, 1. So you can see, let's focus on the polarity. If the polarity is 0, you would see that the idle state is actually low. So this is low, you have the idle. This is low, you have the idle. And you can check it all over when the clock polarity is 0. When the clock polarity is 1, here and here, then the idle is actually when the clock is in the high level. Now, let's look at the edge. For the edge, we have the clock E or the clock edge select bit. If it is 0, then the serial output data, we are talking about the output data. So the serial output data will change on the transition from the idle clock to the active clock. If it is 1, then the serial output data changes on the transition from the active clock to the idle clock. Now, between those two, which format is used depends on the peripheral, and the polarity 0 clock edge equal to 1 seems common. This case is actually here, which is this one. So that one is kind of more common, but it could be any one of them. So let's check the edge again here. For the edge, if the edge is 0, then you are moving from idle to active, and that's actually here would be a rising, since it's the idle followed by active this way. So you are in the rising edge. And for this case, it's again from the idle the active, but now it will be in the falling edge. If it's 1, then it's the other way around, from the active to idle. So now you have falling in this case and rising in this case. Now, notice the changes here that we said, the rising and the falling. How is this affecting the SPI communication? It affects actually the SDO, which is whatever you want to transmit. So here you have it at the rising. If the clock edge is equal 0, so actually here, if it is 0, whatever your choice, whether it's rising or falling. So if the clock edge is is 0, then you are talking always about this edge here. And you can follow it for next clocks, for the other clocks as well. So you will start putting the first output bit, that's the most significant bit, followed by the next one, followed by the next one, and so on. Now, if the clock edge is 1, then now you are talking about this edge right there. And this is what will happen. So you will output this bit, followed by this bit, followed by the B6, followed by B5, 4, 3, 2, 1, and 0. If you see the difference in the SDO, you won't see much difference except at the end, and it's not that critical. From these choices, 0, 0, 0, 1, 1, 0, 1, 1, 1 of the polarity and the edge, you can see that we are transferring 8 bits in all of the cases. And the difference in these two, you are actually putting the bit out or serially transmitting the bit at the beginning of the clock cycle. So you can see here and here and here, those edges is happening this way. Similarly for this way. While in the other two, you are actually transmitting or you are clocking the bits out at the end of the cycle. At the end of the cycle. You can think about it this way. Now for the SDI, on the other end, what will happen? For the SDI, you need to sample the bits to be able to read it or receive it. And this is why we need the sampling bit. If it is 0, then the input data, now we're talking about the input data. The input data sampled at the middle of the output time. So this is the relation of the input data compared to the SDO. Sampling SDI bit compared to the SDO bit. If it is 1, then the input data sampled at the end of the data output time. So let's say that we have S and B is equal to 0. So you always, for the SDI, you sample at the middle, always. But compared to the output, it's also in the middle. You can see the middle of the output. And here you have also in the middle. Now, if the sampling is equal to 1, again, you always sample the SDI in the middle, but compared to the output, you see that it, in relation to the output, it's at the end of the output bit. That's the difference between the SMB equal to 0 and the SMB equal to 1. Again, you have the SPI interrupt flag. It's always 0 until you finish the communication. You send all the 8-bit, and then whether you send it or receive it, it depends on the current communication. You will raise the interrupt flag at the end of the communication. Now, we said earlier here when we talked about the hardware that we have different buffers. We have the SPI shift register, we have the receiver and transmitter, and we have the SPI buffer. So let's start with the transmission, with transmitting or outputting the data from the bus to the SDO. So here we need to move to the SPI buff first, and then the transmission buff, and then the shift register, the SPI shift register. And this happens looking at the block, the transmission format waveforms. Here, you will start with 0. Once you have this rising or this pulse, at this edge, you will write to the SPI buffer. And then after that, when you fall down here in this clock, you will write whatever was in the buffer to the SPI transmission buffer, which is the buffer on top of that. And then at this edge, you move the whatever in the transmission buffer to the SPI shift register, and you start doing the shift register bit by bit. Now, at that edge here, the user writes the new data in the SPI buffer and repeats the same thing again. Now, for the receiver, actually this waveform, it's in the SPI transmit buffer full. This is one of the status bits. We have also one for the receiver, SPI receiver buffer full. It's actually, if you look at this and you flip it horizontally, you'll come up with that one. Here you will read the SPI buffer first, and in the other edge, whatever in the shift register will be moved in the into the receiving buffer. Now, this is actually details that happens inside the SPI module. What we are interested on is the way we set up the communication, the SPI communication, by adjusting the edge value, the polarity value, and the sampling value in each one of these control bits to know whatever waveform that we can expect. Once it's done, we just look at the interrupt flag. When it is 1, then everything is done. The internal movement, we don't really give it much attention. So let's go back to see what happened when we talk about this one. So here we have the edge is equal to 1 and the polarity is equal to 0. So it's 1, 0. And that's what we had here. 1, 0, which is the common case. So we will have 0 and then 1. Here we have the edge, 0 and then 1. Here we have the edge, and so on. And this would be the idle. This one would be the active. And that's what we had here. You can see that we had an idle And now we have active and so on. And we have the edge actually right here from the active to the idle. That's what we had in there in the timing data. From the active to idle, we have the following. So that's based on the communication. The other one is the SMP. The SMP here is equal to 1. So you sample for the SDI always at the middle, but compared to the output, it's at the end of the output bit. That's why we use the SMP equal to 1. So based on these three options, we had this waveform. Now, at this point, let's move to the control register. We have the SPI1 control register. We say SPI1. Maybe you will have 2 or 3 SPIs in the microcontroller. So the SPI1 control register number 1 have these fields. The important one is the pre and the S-pre fields. Notice that this is 2 bits and this is 3 bits, and it's listed as we discussed in the table, followed by the master mode enable bit, this bit, and if you choose 0, then you are in slave mode. If it is 1, then you are in the master mode. We have the clock polarity, the clock edge, and the sampling. And we already know this. That's for the polarity. This is for the edge. And this is for the sampling. This is exactly what we discussed before. So now you know the location of their fields. We have also here the SSEN, the slave select enable bit. That's in the slave mode. If it is 0, then the this bin, the SSX, is not used by the module, and the bin is controlled by board function. If it is 1, then you would use this bin. What we will use, we'll always have this value as 0, and we will use our on-chip select to indicate what slave we want to communicate with. Other than that, we have the mode. We have mode 16. And this make the choice between a byte and a word. If you use 0, then you are doing it a byte mode, which is only 8 bits. And this is following the example that we've discussed so far. If you choose to have a word, which is 16-bit, you can use it by adjusting this mode 16 field, and you make the value equal to. That's the control, the SPI control register. We have also a status register. We have the SPI receiver buffer full, the SPI transmitter buffer full. They are only red. You can see the R here. There is no W for the right. And for the SPI receiver buffer full, if it is 0, then the receive is not complete, and the buffer is empty. If it is 1, then the receive complete, and the buffer is full of data that you can read. For the transmission, if it is 0, the transmit started, and the SPI transmit is empty. You are actually trying to start the transmission. It's not full yet. If it is 1, then the transmit not yet started, but the SPI transmission is actually full. We have also another status bit, which is the SPI receive overflow. The receive overflow flag bit, if it is 0, everything is fine. There is no overflow. If it is 1, it means that there was an overflow. We received something, and probably there is this card along them. We have the SPI SIDL, and we we have this bit in many of the modules, and we said that we are not doing this, so we'll assume that it's going to be 0. For the SPI enable, usually always in the most significant bit, the SPI enable, if it is 0, notice that's it's readable and writable. So if it is 0, then you disable the module. If it is 1, then you enable the module. These are the special function registers associated with the SPI module. Now, let's see how to program the SPI module. So here, actually, we have only one function that we need besides the configuration. This function, we will use it for both transmitting and receiving. We will use it for both dealing with the SDI and the SDO. It's called IO master SPI1. And you can see that you have an argument and you have also a return value. If you are trying to transmit, then you should give this function in the argument whatever byte or word that you want to transmit. So it's expected in the argument. If you use this as a receiving function, then you will enter here a dummy value. You are not going to use it because you are expecting something actually. And then whatever is this method return for you, you return it in the return value. Now, if you go and check the statements here, once you come here, first you need to clear the SPI interrupt flag because it's expected that it is actually 1, so you make it 0. And at the beginning, it should be cleared. In case you want to transmit, so whatever character here that comes to you from the bus, from the microcontroller bus, it will be written in the SPI buffer, SPI1 buffer. And this is the buffer that we use in the programming, as I specified earlier. And then it will move forward until it moves to the shift register, and then serially, bit by bit, it's going to be transmitted. And then after that, you wait for the operation to complete by going through this while loop. While the SPI 1 interrupt flag is 0, you keep doing this. Once it becomes 1, then it means that the transmission is done, and that's it. You're done with the transmission. If you want to use this function as a receiving function, then first you should check the receive error. So you go here and check if there is something wrong with the receiving. If the SPI1 status bit SPI receiver overflow, if there is an overflow, then what happens is you are trying to receive, but you are still full. You cannot receive the new information. Then you would reset this flag and probably show a message there is a problem, there was an overflow, or simply discard it. It will be overwritten, and don't worry about it. Now, what will happen in the receiving side? This will be a dummy value, zeros. So you will send something like zeros. Anyway, if there is no error, you will go here and then you will check the SPI interrupt flag. Now you are receiving. If the interrupt flag becomes 1, it means that the receiving is done, and now you can return the value over here. So you can see here that this method, we used it in both ways, for sending and also for receiving. Notice here that it says that it must always read the input buffer or the SPI overflow can occur. This is why you need always to return it. This is an example, and you can see here the transmission initiated by the master. The master controls everything. The slave is just follow whatever the master is doing. So here, the master is sending a string to a slave. So what happened? The master sent the message. There are actually only 3 letters here, or 3 bytes. The master sends in the SDO M, and then it sent S, and then it sent the 000 indicating the end of message. The SDO of the master is connecting to the SDI. Now, at the time specified here, where you send the message or the byte M, the slave will output zeros, which are actually dummy values. So whatever is master, it's like a common pipe that moves from this direction through the slave to this direction. So whatever you are pushing here, it will come out here as zeros. This is for the send. The important part here is the master is sending this message to the slave. Now, what about the other way around? Now, let's say that the master here is reading the reversed string from the slave. So the slave did some work on it, some processing where it flipped the message. So it replaced the M by the S and the S by the M. So here, the master must send zeros in the SDO. It sends zeros followed by zeros followed by zeros. And every time, the SDO is actually of the slave is pushing the new string after reversal. So the master will receive the S first, followed by the M, followed by the end of value. Now here at this point, the master must send dummy zeros so it can receive the important data that the slave was able to pass to the master. So to read data from the slave device, the master has to write data in order to get it back. Now let's have an example. This example actually is interfacing the PIC24 as a master with a serial EEPROM, namely the 25LC080P, which is this one now, an EEPROM. It's actually a serial EEPROM, and it's a slave. If you remember, when we talk about the memory, we detailed the parallel memory to you. And we said that we will push the serial memory or the serial EEPROM to the this lecture when we talk about the SPI. And that's what happens here. Same 4 wires for the master, and now they are connected to the EEPROM. The SDO is connected to the SI. The SDI is connected to the SO. So now the direction is this way. And the clock and the chip select is provided by the microcontroller and sent to the EEPROM. Now for this EEPROM, it's accessed serially using the SPI with the maximum clock speed of 10 megahertz. That's the specification of the EEPROM. The organization is 124 times 8-bit. However, the transmission is happened serially bit by bit. And it can write maximum of 1 page at a time if the page is 32, and the page also is the 32 byte. Now let's look at the bin diagram. Now for this one, it's shown only 4 bins for this EEPROM, but actually it has 8. We have the obvious, which is the SO, SI, and S clock. And we have also the chip select. We already discussed this, and it's the same way for the EEPROM. The SI for the serial data input, the S clock for the serial clock input, the chip select, it's active low, it's for selecting the EEPROM, and the SO for the serial data output. We have the VCC and the VSS. The VSS is the ground, and the VCC is the supply voltage. So now we covered 6 pins. There are 2 more pins that are kind of control pins. One of them is the write protect, and it's active low. So if you activated the write protect, so it's meaning that the value here is 0, you are protecting the EEPROM from any changes or updates. There is no writing. For the hold, it's also active low, and it's holding the input. It's for holding the input. Now, remember, this is the microcontroller, and it has a microprocessor that can execute instruction. Here we have an EEPROM, and the EEPROM now is an entity that is connected to the microcontroller. There is no CPU inside it. So it needs the microprocessor to tell it exactly what to do. So there are certain simple instructions that the EEPROM can understand. These instructions are detailed in this table. We have a read and a write. Read for reading the data from the memory array, beginning at a certain address. We have a write the data to the memory array, beginning at a selected address. So the memory expects an address and expecting an instruction, whether it's read or write. If the memory see this instruction, 11000000, which is 3 in hexadecimal, it knows that there is the microcontroller or the microprocessor of the microcontroller is asking for reading the data. If it sees this, which is 2 in hexadecimal, then it expects a write. We have other instructions. We have the write disable and the write enable, which resets the write enable latch or sets the write enable latch. The write disable, it will disable the write operation. The write enable will enable the write operation. And we also have status register, one for the read and one for the write. And you can see the name of the instructions or the value of the instructions. Here we have 4, here we'll have 6, here we have 5, and here we have 1. The important ones that we will see in the following program is the read, the write, and the write enable. The read and the write and the write enable. So here we said that we can read the status register. This is the status register. It's from 0 to 7 bits. So the total is 8 bits. It has the WIB, WEL, the BP0, the BP1, and the WBEN. What are these status bits? 4, 5, and 6 is not used. So each one of them is described here. We have the WIB, which means it's actually a status. It's only readable. It tells you that the write is in progress, indicating that it's busy. So if you see 1 here, it means that the write is in progress. We have the WEL, which is the write enable latch. It's actually a bit indicating the status of the write enable latch. We said there are certain instructions that enable this latch. We have the write disable and the write enable instruction, and this WEL it tells you the status of that latch. So we have the write disable and the write enable, and these two instruction directly affect the WE. So when it's set to 1, the latch allows the write to the array or the status register. When it's set to a 0, the latch prohibits the writes to the array or the status register, and these two instructions deals with it. We also have two bits for block protection. You are actually protecting the EEPROM, and these bits indicate which blocks are currently write protected. Since there are two, there are 4 choices. Either 0, 0, which means no protection, or 1, 0, which protects quarter of the EEPROM, beginning from the high address. And then if it is 0, 1, it will protect half of the EEPROM, which is the one from the middle to the high address. And if it is 1, 1, it will protect the whole EEPROM. For the this bit, the WBEN, that's the write protect enable, which enables the protecting of against the write using the pin that we described earlier. This write protect. So after knowing this, we want to send some meaningful bits so we can read or write from the EEPROM. To do that, this is the way you read from the EEPROM. You would send the instruction first, followed by the address, and then you expect the data to be output to you. Notice that this is a serial clock. Bit by bit, you would send the most significant bit of the instruction first. So you would send 0, 0, 0, 0, 0, 0, and then 1, 1. Now you send the instruction, and you know that this instruction is read. You go back here, you know that it is read. So now the EEPROM knows that it expected a read operation. It expected an address following that. The address is 16-bit. 16-bit address from 0 to 50. So you give the address here, again, the most significant bit first. And then once you're done with the 16 bits, the memory should give you the output, bit by bit, starting from the most significant bit. Now we were able to read a single byte. And you can actually exactly calculate how much time you need for the whole operation. If you know the amount of the time for a single clock here, and you know the frequency, that you should know the frequency, which is the serial clock. If you take the reciprocal, you can get the time here. And then count how many cycles you have. For this example, we have 31 cycles. So you multiply 31 by the reciprocal of the frequency, and you get the time for sending or for reading 1 byte. What about the write? Compared to the read, focus on this region here. This is the instruction 1, 1, and then you have zeros. For the write, it's actually 0, 1, and then zeros. So the difference on the instruction. Now the EEPROM will expect the address and also the data that you want to write. Notice that all of this should be in the SI, which is the serial input. This is the serial input of the EEPROM. So it was sent from the SDO of the master, the microcontroller, and it is received at the SI of the EEPROM. Now in the SO, there is nothing getting out of the EEPROM because this is a write operation. only in the read, this is the previous slide, only in the read, the SO will show the data. Now, this is for writing a single byte. How about if you want to write multiple bytes? Similar thing for the read as well. What will happen? This is what will happen. You can compare slide 14 with the next one, 15. You see that here, we follow the same thing, but we send the first data byte, followed by the second, by the third, and up, you have up to, for that specific EEPROM, you have up to 32 bytes. Some other memory may be up to 64. It depends on the memory. And you can get all of this information from the data sheet. If you go to the data sheet of the EEPROM, you will see this. You will also see more than that. You will see the bin diagram, the electrical characteristic. You can also see some timing diagrams as well, and so on. Again, here, notice that we will send only the address of this first data byte. And then the EEPROM understand that you need more data bytes. At this point, we finished discussing the SPI module, and we just need to give you an example. This is one example. Let's say that you have a big 24 operating at the frequency of oscillation 80 megahertz, and it is interfaced to an SPI or a SPI memory device. This is the memory, and we've discussed this before. Now, the specifications are as follows. The SPI clock speed is 5 mega, and you can compare this to the FOSC. It's much lower. The clock idle is high. This helps me specifying the polarity and also the edge. The information will come. So the clock is idle. The clock idle is high. That's the for the polarity. And it's an 8-bit mode. It's not 16. It's only 8. Master mode. So you need to configure the PIC24 as a master. The output changes when the clock changes from idle to active. Now you know the edge. Along with this information, these two information, you can specify the edge and the polarity. The chip select is connected to RP3, as you can see. The SDI and the SDO and the S clock are assigned removable pins that you can see here as well. Now, there are two requirements in this example. The first requirement is configuring the SPI, getting the SPI one control register, and you should give a possible setting for the SPRI and the PPRI, the edge and the polarity, and the other fields as well. That's the first requirement. The second requirement, you are required to write a code to read from and write to this EEPROM. Remember, to deal with the SPI, we have only one method that we use, which is this method, that one that we discussed. We just call this method, which is the IO master SPI 1. That's what we call. Okay. So let's begin by configuring the SPI based on the requirements. Not all the requirements are given. If there is certain requirement that not specified or not important, you can assume whatever you like. Some of them, even if they are mentioned, is inherently known. So even if somebody didn't tell you anything about the master mode, you know, since this is the microcontroller, it's supposed to be a master, and this one supposed to be a slave, which is the EEPROM. So let's see that. First, we will set up the PPRI and the SPRI. I repeated or showed the tables again. As you know, the PPRI, we have 4 values, 1, 4, 16, and 64. So we follow the equation. This is the specification we said. This is the value of the FCY. The FOSC was 80, so the FCY is 40 meg. This is the value of the S clock, the 5 mega that was given. And we try 1, 4, 16, and 64, as you can see here, 1, 4, 16, and 64. So we try all of them, and we calculate the SPRI. we assume the B-pre and calculate the associate or the associate S-pre value. For this one, for this case, it's 8. For the other case, it's 2. For the following case is 0.5, and the last one is 0.125. Remember, in the S-pre, we can only set it, as you can see here, integers. 1, 2, 3, 4, 5, 6, and 7, and 8. These are the possible options. Even though it's mentioned here that all of these are valid, the last two, they are actually fractions. So if you round them up to 1, actually you will lose some of the frequency for the serial clock. So you should choose the one that gives you an integer value following the S-pre. Sometimes I could give you an example that you will never have any integer value. So you will round up, and the best round that you got will give you the best frequency. So here we choose actually the S-pre to be 2, which is this case. So in this case, the B-pre is 4 and the S-pre is 2. And if we plug them here in this equation, the original equation, we would say that this is 40 meg divided by 8, 2 times 8, 4, which equals to 5 megahertz, which what we expected. This was given to you. So this is only for checking. Now we know that the S-pre, P-pre pair is 2 and 4. The S-pre is 2 and the P-pre is 4. This is what we want. Now to get the binary value, we consult the table. Make sure you go to the table. So here, for the P-pre 4, this is the P-pre 4, and it gives you 0, 1 in binary, so that's it. For the S-pre, we have 2, and 2 is 0, 1, 1 in binary. It's not a conversion from decimal to binary. It's totally different. So you have to consult the table. Now, because the clock is actually from idle to high, and the output changes when the clock changes from idle to active. So the clock is, or the clock idle is high. From the 4 options, the idle, when it's high, it's either this case or this case. Now, we want the output change from idle to active, which is going to be this case, from idle to active. The following, which is this one, which is the clock edge is going to be 0, and the clock polarity is going to be 1. The other things or the specification that were given to you, it's 8-bit and a master mode. And if you look at the details, I put it in a small table here. We know that the S or the P-pre is 0, 1. That's 0, 1 here. We know that the S-pre is 0, 1, 1. So it's 0, 1, 1. Followed by this 5th bit, which is the master enable. We said that it's master, so it's supposed to be 1. Followed by the polarity and the edge and the SMB. The polarity is 1 from idle. The idle state is actually at the high. And for the bit number 8, the edge, we make it 0. So the output changes from the idle to active as specified. And for bit 9, we choose 0. For the sampling, we choose 0. So actually, it's at the middle of the output. We always sample the SDI at the middle, but compared to the output, is also in the middle. And I don't think it was specified in the requirements. We didn't say it here anywhere. So we just assume that to make it 0. And for mode 16, since we used 8-bit, it has to be 0. For the other bits, since we didn't specify anything, we assume also they are 0. So from this value in binary, in hexadecimal, it becomes, this one is A, this one is 7, and the rest are 0. So we have A700 as the SPI control register value. And now to do the code for reading and writing this EEPROM, we need to make certain configuration. First, we define the chip select, we call it EEPROM underscore chip select, and we chose lat B3 as it was shown in this block diagram. So that's the RB3. This is why we choose it here. We configure it. It has to be an output, since the chip select direction is selecting whatever the EEPROM. So the direction is from the microcontroller to the EEPROM. So that's an output. So the trace value is equal to 0. And we also set up the associative or the associative, the associated multiplexed change notification and analog signals. We disable the analog, or the pull-up enable or the change notification value for it is actually, the bin is number 7, and we make it equal to 0. So this way we configure this chip select. For the other values, to configure them, we configure them inside this method or this macro. First, the SPI control register. This is what we found, A700. And now we will use the remappable pin for the SDO. That's the way. We say RP6R equal to 7. That's the remappable pin number. And that's the code for the SDO, which is 7. For RB7, that's the clock. Again, we choose 7. That's the RP number, and that's the code for the S clock. The name of the SDI, since it's an input, is called underscore SDI 1 register, and we say that it's equal to RP5, which is this. Now we set up all of these 3. We make the chip select equal to 1 to select the EEPROM, and then we start the SPI module. We're done with the configuration. We define some instructions: the read, the write, and the write enable. These are the important instructions based on this table. So the read is actually 3, the write is 2, and the write enable is 6. We will use them in the read and the write methods. After that, we prepare the write and the read. And then after that, we should be able to use them in the main code. Now, for the write, what we're trying to do in this program is following what we specified here. This is for the write, and this is for the read. Whatever we have here, we will try to do it in the code. So we should send the instruction, followed by the address, followed by the data R for the read. So we send the instruction and the address, and we are supposed to read the data after that in the from the serial output of the EEPROM to the SDI of the microcontroller. Before that, for the write, we expect the instruction followed by the address followed by the data. And if you have multiple data bytes, then you can have that as well. But you need to enable the write by using the instruction write enable. This is what we will do here. So in the write, first we select the chip. In the beginning here in the configuration, we make the chip select equal to 1, so it's not selected, it's actually disabled. Whenever we do certain operation with the EEPROM, we sandwich it between EEPROM chip select equal to 0 and EEPROM chip select equal to 1, between these two. Here we use the method that we talked about, which is the IO master SPI1. And we give it the instruction write enable first to enable the write. That's the first piece of data that we send to the EEPROM. We enable the write, followed by the write instruction. That's 2. Notice that we always sandwich between chip select equal to 0 and chip select equal to 1. This is activating the EEPROM, and this is disabling the EEPROM. Similarly here, chip select equal to 0, chip select equal to 1. Actually, we could have take this out, both of them, but I kept them since you might have certain things that you need to do in between. And this is maybe you will do something that is not related to the EEPROM with another method. If that's the case, then we do it this way. Otherwise, just take them out and have only one chip select. You activate it at the beginning, do whatever you want to do with the EEPROM, and then disable it at the end. Now we have, after the write, we send the address. We know that the address is 16 bits, and we chose the mode to be 8. So we will do it in two steps. The first step is the upper half of the address from A8 to A15. We will send the address shifted to the right, but by 8-bit. That's the upper half. And then we will send the lower half, which is the address bitwise ended with 0xFF. Now, this way, we send 16-bit address. That's the third step, sending the address. And the fourth step, which is this for loop here, we will send the data one by one. So whatever length you have, you will here send the address for the write, and you send the buffer with its length. So you send actually an array of members with their length, and you want to write them into the EEPROM. So once you prepare step 1, 2, and 3, and 4, you go through the index of the buffer, and you would send them one by one. Buffer 0, and then you increment buffer 1, increment buffer 2, and so on until the end of the buffer. That's for the write. For the read, we have a function that is send the EEPROM read address only. We just need to send the address, and then in the main code, we will read the data. So here we will sandwich between the chip select, and we will send the read instruction, and again the address in a similar way like the write. We send the upper half first and then the lower half. We didn't read yet, we just sent the address. The reading will happen in the main. So now in the main, I could do, I could call these methods, write the EEPROM, and send the EEPROM read address, and work with that. So let's check that. In the main code, we have make the buffer 32, and we want to do certain operations. So we configure the EEPROM chip select, we configure the SPI, and the first, at first we initialize a buffer from 0 to 32. That's the size of the buffer, and we had certain dummy values, I times 5. It could be any values. We populated the elements of the buffer, and now we write to the EEPROM. Starting from address 0x0000, that's the first position of the EEPROM, we will write the buffer, which is 32-bit. Whatever you populated, you will write it to the EEPROM. And since we already discussed this method, it will write all the values into the EEPROM by using this part. Now, next, we chose to write another 32 bytes, which is basically the same buffer, but starting from this hexadecimal address. Now, this hexadecimal address is actually 0000, and this too is 0100. So that's the, if you want to find the decimal value of this address, you would say 1, 2, 4, 8, 16, and 32. So you will copy 32 elements from 0, 0, 0, 0, all the way to the location just before this address. So you fill up 32 members of the buffer, and then you have another 32. For reading the or the read operation, here we chose to use the EEPROM chip select, but it's not necessary since we already did that here. So it's actually not necessary to do this. Now we send the EEPROM read address. Notice that we send the address that we want to read. So we want to read the value from this position 0x5000, and we went through a for loop, and we want to accumulate the values. We want to sum them. So here we have a running sum. The sum is equal sum plus IO master, and now we give it a dummy value. Notice that we are using the IO master SPI1, and we are giving that a dummy value. If you send a dummy value using the IO master SPI, then the EEPROM will send you the values one by one, and this way you can read them as the microcontroller. Since you use this function, now you need the EEPROM chip select. You must activate it here, and you disable it here. And then at the end, you do while for it. At this point, we finish the example for using this SPI. And now we covered the UART as an asynchronous serial communication. We covered the SPI as a synchronous serial communication. And it's actually from my experience, it's more common to use the SPI more than the UART. For the I2C, you can cover it yourself. There is certain fields that you need to worry about, and there is a certain communication way. But since it's only 2 wires, it's supposed to be easier for you. And now we're done with the communication modules. Next time, we will discuss the last module of our microcontroller, which is the analog to digital conversion module. I will talk to you next time.